Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today, we have Sarah McCarty, who is a PhD student at Iowa State. We are happy to have her here today to tell us about shallow ReLU neural networks and their representations of piecewise linear functions. Take it away, Sarah.
Hello. So I will be talking about shallow ReLU neural networks and the representations of piecewise linear functions. While you might not know what all these terms mean yet, in 2019, Ongie conjectured that every piecewise linear infinite width ReLU shallow network is representable as a finite width shallow network. And the exciting thing is that that is true. So today we'll talk about what this conjecture means and its implications and the ideas of the proof. So we will start with the conjecture. Finite width shallow networks are complex functions f from Rn, as in complicated functions f from Rn plus 1 to R that are built out of a really simple activation function. So you take your input x, you take your choices of parameters ai and bi. You plug ai.x minus bi into sigma, your activation function, and then you weight your choice of parameters with ci. And throughout this talk, the activation function we'll use is ReLU, which just takes negative numbers to 0 and positive numbers to themselves, such that the only place it does anything interesting is at x equals 0. And this whole class of finite width networks will denote NFIN, and it's a popular class of functions to do everything from assigning probability scores on cancer to classifying images. But you do want to have some sense of the complexity of a network. And while this is a bit of a squishy concept, one way to quantify that is by the size of the parameters. So you sum the magnitude of ci times ai for all of your parameters. But you can keep the complexity of a network constrained even as you let the number of distinct parameters, k, get larger and larger. And when you let k go off to infinity, that's when you get infinite width shallow networks. So what has happened here is our sum has been replaced by an integral. We still plug a.x minus b into sigma, but now we weight our choice of parameters with mu, a measure on our parameter space where the a's come from the unit sphere and b is a real number. And we can call this whole class of infinite width functions n sub infinity. We let our measure be signed, it'll be a Borel measure, and now the total variation of our measure mu corresponds with the sums of the size of our parameters in the finite width case. So to keep the complexity of our network constrained, we're going to have mu be finite. Every finite width network is representable as an infinite width network by using point masses at the right places in the measure mu. And we understand finite width networks much better than we understand infinite width networks. So it'd be nice to be able to extend results about finite width networks to infinite width. The first thing we know about finite width networks is that they are always piecewise linear, but not all piecewise linear functions are finite width networks. And one of the key pieces of criteria that you can tell is if you look in the domain of a piecewise linear function and you break it up into the different affine pieces, you'll have these boundaries here in black. And for it to be a finite width network, you want those boundaries to be entire hyperplanes. So in R2, you want it to be entire lines, like on the left. You can have piecewise linear functions where you have part of a hyperplane, and then it stops and it breaks up into different hyperplanes, and that cannot be represented with a finite width network. So what the conjecture said was every piecewise linear infinite width shallow network is representable as a finite width network. So to put that into context of what was already known, we have finite width networks. We know that they are representable as infinite width networks and that they are piecewise linear. So this is a containment. There are non-piecewise linear infinite width networks. So this is properly contained in all of n infinity. And all infinite width networks are continuous, but we're certainly missing some. In fact, n infinity is missing some piecewise linear networks. So this is also piecewise linear functions. So this is also a proper containment. And what the conjecture is saying is it's talking about the highlighted relationship. And it's saying, unlike all of the other containments on this diagram, this is not a proper containment, this is equality. And we can characterize piecewise linear infinite width networks with finite width networks. And as promised, this conjecture is true. So I hope to show you why. In part 2, the proof. So we're looking at a measure mu that induces a piecewise linear network, an infinite width piecewise linear network. And just like any measure, we can decompose the measure into the atoms, which are the point masses of the measure, and an atomless part of the measure. And the atomic part of a measure is essentially a finite width network. So we know that mu atoms will induce a piecewise linear network itself. And since mu also induces a piecewise linear network, in fact, mu atomless must induce a piecewise linear network. And since we know that the atomic part of the measure is essentially a finite width network, we want the atomless part to go away, because that's the part that we can't represent with a finite width network. And we'd like it to be 0. So our goal is to prove that whenever we have an atomless measure that induces a piecewise linear network, as happens here, our measure is actually 0. And this means that in an infinite width network, the part of the measure unique to an infinite width network cannot provide anything new to a piecewise linear function. So we're trying to show that this atomless measure on the sphere across R is 0. So how can we tell if a measure is 0? A tool available to us is the Kramer-Wald theorem, which says a finite measure on Rn is uniquely determined by its values on half spaces. So if our measure mu acts like 0 on all of these half spaces, it must be 0. But while our measure is a finite measure, mu is not on Rn. Mu is a measure on the sphere across R. So to fix that, we're going to want to project the sphere onto Rn. And with a sphere, you can do a rectilinear projection, where you start with the sphere, you put the tangent hyperplane, which is a copy of Rn, on top or bottom of the hypersphere. And then from the center to any point in the sphere, you get a line, and you can follow that line to wherever it hits the tangent plane. And this is a very nice projection. But looking at this picture, you might notice 2 problems. Problem number 1, rectilinear projection doesn't work with the green points along the equator of the sphere. Those end up being a small enough part of the sphere that we can ignore that issue as a technicality. And problem number 2 is that we are not projecting onto 1 copy of Rn, we are projecting onto 2 copies of Rn. And how that is handled is that the sphere has so much symmetry, and how parameters that are antipodal on the sphere interact with behavior in your network F has so much symmetry that it's actually sufficient to consider only one of them. So we'll look at this projection phi plus, which takes the upper half sphere onto Rn. And we'll think about the measure that phi plus induces, and we'll try to show it's 0. And in order to apply Kramer-Wald, we need to think about what are half spaces with this projection phi plus. So we have a point A on the top half of our sphere, so the last coordinate is positive. And what phi plus does is it takes A, B, and it takes A1 through AN in B, and it divides all of it by AN plus 1. Almost every half space, which is enough for our purposes, and Rn cross R, is either of the form HZ, where Z is whatever number you'd like, and Rn cross R, and HZ is the set of all alpha beta, such that Z dot alpha concatenated with 1 is greater than or equal to beta, or it's the closure of the complement, which is what you get by reversing the inequality. So investigating what half spaces look like, we observe that phi plus of AB is in our half space HZ, if and only if it satisfies this defining inequality of HZ. And AN plus 1 is known to be positive, so we can just multiply that out. And this happens if and only if Z dot A is greater than or equal to B. And that's equivalent to saying the hyperplane HAB, defined by the equation A dot x equals B, intersects the ray RZ, where this is the ray that starts at Z, and then we let it go down in the last coordinate. So pictorially, what's going on here is we have a point Z somewhere in Rn cross R. We have the ray RZ, which goes down in the last coordinate. And then each set of parameters A and B is associated with a hyperplane, HAB, that's A dot x equals B. And since this is in R2, hyperplanes are just lines. So when we're thinking about a half space, we're thinking about all the parameters associated with lines that intersect RZ, so the lines in blue, and not the parameters associated with lines that don't intersect RZ, the lines in gray. And we can get a wide variety of different half spaces by moving Z around. And if we had flipped this inequality, all that would have happened is our ray would have been pointing up instead of down, and all would work out much the same. So now that we know that half spaces are these sets of hyperplanes intersecting a ray, we want to show that the measure mu acts like 0 towards these half spaces. And you can act like 0 by having the integral over your half space, so hyperplanes intersecting ray RZ, of a strictly positive function, AN plus 1, being 0. And so we want this integral of AN plus 1 to vanish for a large set of different Z, because that's a large set of different half spaces. Now, our ray RZ can be put inside of the domain of our network F. And the domain of our network F can be broken up into polyhedra, open polyhedra, on which F is affine linear. And so these black lines are denoting the boundaries between those open polyhedra. And you can very naturally decompose a ray into the segments contained inside an open polyhedra and the red points where the ray intersects the boundaries between these open polyhedra. The boundary points end up being such a small part of the ray that if you use some cool algebra tricks that we don't have time for today, you can pick a large set of Z where the sets associated with the boundary points always have measure 0 and don't matter. And so that means that we can pick a large set of Z, if we're careful about it, where the integral over the hyperplanes intersecting a ray RZ equals just the sum of the integrals of the hyperplanes intersecting the ray inside each of these open polyhedra. And we're hoping to show that this integral vanishes, and so we can do that by showing each of these individual integrals inside of an affine piece vanish. We have been integrating an plus 1, and an advantage of doing that is the integral of an plus 1 over hyperplanes intersecting a ray x actually turns out to be the first directional derivative in the vertical direction of f at the point x. So for example, in this picture, if you wanted to compute the derivative of f at z in the vertical direction, you could do that by computing an integral over this ray rz. We are interested in this integral of hyperplanes intersecting the ray rz inside of the affine piece A, which is highlighted in green. And we can see that rz intersect A is going to be the ray rz minus the ray rz prime, where z prime is where the ray rz intersects the boundary of A. And this means that we can break up our integral similarly into the integral of hyperplanes intersecting the ray rz minus the integral over all those hyperplanes intersecting rz prime. But there's a small hitch in that we really want both of our points to be properly inside of affine piece A. So we're going to bump z prime up just a little bit in the last coordinate by adding epsilon en plus 1. And we're going to let epsilon go to 0. And by our lemma, we know that this first integral is the derivative of f at z. And the second integral is the vertical derivative of f at z prime plus epsilon. Since z and z prime plus epsilon are in the same affine piece, they must have the same derivative. Their difference is 0. This limit must be 0. And our integral must vanish. And so now that we have all these integrals vanishing, we know that the atomless part of our measure, the part we can't replicate with a finite width network, is in fact 0. So an interesting corollary of that fact is that there does not exist a non-trivial, compactly supported, piecewise linear shallow network on Rn whenever n is 2 or larger, even if you go to the infinite width. So the kinds of functions that we're talking about would be something like this. We have a nice little piecewise linear pyramid, but then it has compact support. And the reason why is just we can directly apply the results we know about finite width networks. Finite width networks, we said you can't have the boundaries between the affine pieces stop, but with compact support, the boundaries are always stopping. In terms of future work, deep networks are what you get when you compose shallow networks with each other. It is known that finite width deep neural networks on Rn are representable as this weighted sum of a max of n plus 1 terms. And the important thing to notice here is that the number of terms we're taking the maximum of, n plus 1, depends only on the dimension of the domain. Further, we know how to represent the max of n plus 1 terms in log base 2 of n plus 1 layers. So what this means is that if you're in the domain Rn and you have log base 2 of n plus 1 layers, adding another layer doesn't add any new functions. And so this provides a kind of saturation point at log base 2 of n plus 1 layers. An interesting question is, does the infinite width case also have a saturation point? One way this could possibly be shown is if it were the case that infinite width networks were always the integral of the max of n plus 1 terms, but that is not known. So here are some references. I wrote a paper with the proof. Ongie wrote a paper with some other results in the conjecture, and Savaris did some early results with lower dimensional domains. Thank you.
Awesome. let's thank the speaker by clicking buttons as we do. All right, I'll stop the recording here.